Okay, can you guys hear and see okay? That are online? You guys are seeing and hearing okay? Anyone online can hear and see me okay? Along with the notes. Thanks, Xavier. Okay. Okay, quick summary. So complex power, average power is this equation, and then RMS, remember that we went through that as if you have a sinusoid, it's going to be the magnitude over the square root of 2. So for any sinusoid, we can now pretty much say we just take the magnitude and square root over 2. If it's not a sinusoid and you need to actually integrate it to find the RMS value, you would use that equation there. And then average power can be found in two ways, either this equation, or usually it's easier to find the complex power first and then take the real part of that in rectangular form to find the average power. So that's usually the way I recommend doing it, is to find the average power that way. So complex power is VMRS, which again is the magnitude of the voltage signal over the square root of 2. And then the IRMS is the complex conjugate. So whatever the J value, you change it to, whatever J value, you change it to negative. So to do this, it's easiest when you do multiplication in complex is to make sure you're in polar form. So we're going to do polar form for VRMS, IRMS is usually the preferred method. So polar form is going to be the easier route to do, and that's missing a star. And then rectangular form to get the real power, which is going to be in watts, and the complex one is the reactive power, V volt ampere reactive, VAR. So this is rectangular form. From these values, you can then find the power factor, and that's going to be the real power average over the magnitude from the polar form. And then you look at the angle in the polar form. If the angle is positive, it means that it's lagging. If it's negative, it means it's leading. Okay? Questions about complex power? Okay. Maximum power. So these were the videos that you got to watch on Monday and Wednesday. Hopefully you guys have gone through those examples. If not, go back and watch those. Make sure you know how to do the maximum power transfer. So finding the Thevenin impedance, it's going to be complex, and then the Thevenin voltage. And then you find the max average power by that equation, if you've put on the load that is equal to the complex conjugate of the Thevenin impedance that you find. Okay, questions on this? Okay. All right, filters. Passive filters and active filters. So active filter is just pretty much when you have op amps in there, transistor, or any other nonlinear device, or what we consider an active device. Passive kind of goes along with that. Okay, low pass, high pass, band reject. So being able to identify what kind of a filter do you have, and then identifying the corner frequencies. So the corner frequency is again 3 dB less than the maximum or flat magnitude. And that 3 dB comes from where? 1 over the square root of 2. So 1 over the square root of 2 in volt per volt translates into 3 dB. So that's where that comes from. So 1 over the square root of 2 times the maximum magnitude is going to be 3 dB less than the MO, whatever that MO is. So that's where that comes in. And now you know why, because that is what we consider as the average for a AC signal. All right, corner frequency is that point that is 3 dB less, or if it's in volts per volt, it will be 1 over the square root of 2. So that's where we consider our corner frequency at that average value. Or I should say root mean square. RMS value is what we consider that corner part. And then the high pass filter is when we started that value and then it's everything greater. And then we have 2 points for band reject and band pass. And so we have 2 corner frequencies. Again, they're the same, 3 dB less than the max. And then the middle frequency is that resonant frequency, omega naught. So you need to understand all those terminologies, being able to identify them on these graphs. And then the last part of this was understanding the Q factor. So the Q or quality factor was if you have a high Q is where you desire it. If you have a low Q, that means that you have a really wide range. It's not really selective of those frequencies. Okay, so that terminology also for low and high Q. Yes.
So in general, like a high Q factor would be ideal for like a very specific band pass or band reject.
Yes.
But you sort of want more of a low Q on a high pass or low pass. We didn't want that sharp spike in sensitivity right before the.
Correct. Yeah. Yes.
Right.
So yes, you are right. All right, any questions about the filters and what you kind of need to know for filters? Okay, so from there we went into finding the transfer function. So to find the transfer function, we are not needing to find that initial value anymore. So you can do it with just 1 over CS and LS for your inductor. You solve to find the transfer function, which is output over input. And then from there, you can change from S's to J omegas to actually convert back to, if you want to do the Fourier transform, and that will encompass both the initial values. So that's kind of the whole methodology. If we're looking, in this case, we were looking at just plotting that, this function in the S domain so that we could get the graph to figure out what does it look like as far as if it's a filter or not. So this was what we graphed, and then we were able to identify the middle frequency, that resonant frequency, omega naught, and then the low and the high corner frequencies. All right, so do you guys have requests of particular problems you want to go over? I can see if I can find any. So you guys, that's all the information for this unit. So now lots and lots of examples. So that's what we're going into next. It's lots and lots of examples. So Monday and Wednesday, there were some max power transfer examples. Any requests for today?
So one of the transform function Fourier transform. Solve one of those, or
If you
Yeah.
looked at the lecture, videos.
So
Where,
Just look at the lecture notes. It'll be fun.
where is it daily lecture notes? Is that the
Like
thing?
what
handouts,
you do is
lecture,
you go to
look
the
at
Unit 3.
example lectures.
You go to the Unit 3 page, and then there will be a link that says daily lectures, and you click on that, and it'll bring up all the slides.
I don't know how that works.
so
Yeah, no,
Com-
I didn't, I wasn't
complex
able to figure
power.
it out until last night, so don't worry.
complex power is what you're looking at for this week. And then max power transfer, I think, for next week. Yeah, max power transfer. And then, trying to remember the,
Well, the homeworks were on max power transfer.
mhm.
Right?
Yeah, yep, and the homework is, was,
On average and one on
Yeah.
was it the same as, anybody taken the quiz yet? So was it the same as the homework?
Yeah, it was like literally
I was gonna say, I think I meant it to be very easy and straightforward, so.
It's like exactly the same.
Okay,
Just like what
so
you
homework,
said.
make sure you got the homework, and then if you can do homework, you can do the quiz this week. Okay. All right, 18, let's see. Okay. So you wanted to go through all the steps?
Yeah.
Okay. All right, so did we start this? I thought we started this one.
I think we may have.
Go back to this one. Yeah, we did start this one. Okay, I just ran through it really quick at the end. Okay, so we started this not last lecture, but last week. We started this one, and in this, it is to go through all of the steps for the Fourier transform. So we don't quite know, would VC actually be a filter or not? So to find out if this was like a filter circuit or what kind of a form it has in that magnitude plot will help us to know, is it one of the filter types or is it some other kind of circuit? So what you would do there is you would find an equation in the S domain for VC. And so that would be this one. Find a different color. So here is your VC equation. And then your input would be considered VS. And so you would just divide over the other side. So you would have VC over VS. And then that would be equal to 2 over 3 plus, that ended up being S, I think. 4K times 0.25 was just an S. So that would be your equation for the Bode plot. For those that have taken 2280, what does this Bode plot look like?
Where's the transfer function? The 3 plus S, shouldn't it be, yeah, S plus 3, so it would be something, it would be a pole at S equals
-3. So that would be where you would be located, and then S equals -3 would be one pole. So you only have one pole in here. So, yes.
Yeah, so it kind of go, it's a low pass filter, and so it would kind of go out around 1 or 0 decibels, and then it kind of goes out to a frequency of around 3 is our corner frequency, and then it goes down about 20 decibels per decade after that. If we go a linear approximation.
Yeah. So this would be down at -20 dB per decade. Slope. So, kind of doesn't look like there, but at 3, so 3 radians per second, remember these are in radians per second, and then your magnitude here would be 2 over 3, yeah. You'd bring out the 3, so it'd be 2/3 volt per volt, and you could change that too. So it would be a low-pass filter. So this is an actual filter. And so you would plot that Bode plot. For those that haven't taken 2280, you would use MATLAB. As I described before, there's functions. That is the Bode function. It was on this one. Is it on this one? Yeah. So you do S is equal to, oh, and you said Wolfram did Bode plots? Is that what you said, Brian?
It doesn't give you the values of the corner
Oh,
frequency
okay.
or anything else,
So in MATLAB, if you use S, you just define S as your transfer function variable. So you do S is equal to TF, meaning transfer function variable S. And then you type out the equation and then do Bode mag. And then it will plot this. And then in MATLAB, which is nice, you can click on these values and then it will bring up a little box that says your X value and Y value. So you can go down to figure out where that 3 dB point is.
Do you post these class notes, like the slides on Canvas, notes or just the video lecture?
I usually do the notes too. Did I forget?
In the same place? Or-
Yeah, so there's two columns. The first column is they're blank note sheets, and then the second column has the filled out ones. So they're the actual notes that I write in here. So that second column in the handouts and lectures. Okay. So that was just a little side note to show, yeah, we could figure out if this was a filter or what this circuit is. So from here, found VC using node voltage, and then IC was VC over the 0.25 milli-S. And so that gave an IC equation for a specific VS. So we did, this first one was A, so this was finding when VS was just 10 U of T. So go ahead and now do with an input of B. And using the equations we already solved for.
instead of volts. So it just means that each waveform transfers in volts. Yeah, just another notation for it. So you put nodes, let's see, did I put 3 nodes? Oh yeah, so there's 2 nodes, and then you do a voltage equation out of each of those. So you were able to do that? So did you understand how to, so you understood how to set it up? So ZL. Find So did you understand how to put the test source on there? Okay, so when you put the test source, your equations are a little different, and then, okay. And so ZTH, you find, because you find the current going in, and then it's gonna be the voltage over that current. Does that make sense? Okay, so that's all that, okay, so it's just, so it depends on how you set up your matrix here. So here I did it in 3. So I had V1, V2, and then IT as a third. Yeah. So I kept IT in there as an equation, because then this would be, so this is to find the open voltage, but then when you find ZTH, you have to put on a test source there. So then this becomes another node, so like you have to sum the current IT going in there, and then this current and that current. So that's where this third equation comes from. And then it's set up as V1, V2, and untest. And then this third row is gonna give you the value of iTest. So once the solution, this third row is the value of iTest. And this is in rectangular form. And so you take that one, so it's 1 over this value. And that's where the 2.5, does that make sense? Okay, so that was where that came from. And so then from there, then you're gonna take the negative of that to give you, sorry. So it's gonna be 2.5 minus 0.75. Is that more clear now where, what those meant? Okay. So I
Well, you solve for VS, right? We're trying to transform back to VOT, right? Or we're trying to class. So we're trying to transform back to VOT. Yeah, the initial question that it asked, you know, we just talked about, it depends, I think it helps us figure out what type of things we have. Okay.
Okay, so I'm gonna copy a few of these down. Okay, so here's our IC equation. And then we're doing this VS. It's really big. All right, so the Fourier transform for that one. It doesn't have one. No, there it is. All right, so I don't know what table you were looking at, Bri. Oh, you were looking at. So this would be the transform. So Vs of S is going to transform, you have the 10 over 2 plus j omega. And so you're just going to multiply these together. So you have 5 times 10 to the minus 4 S, or sorry, changing to j omega, all over 3 plus j omega times 10 over 2 plus j omega. That's the other one. Sorry, I don't know if these are in my notes. Times EJ. Okay, so then we're going to want to use partial fraction expansion to solve this one, right? Because we have 2 components on the bottom. So with this, then we were going to move to having, and so we moved to the omegas, so you have omega in here. And so this is going to be I'm just gonna do it up here. And then this is gonna be equal to A over 3 plus j omega, and then B over 2 plus j omega. So we're going to use the same technique that we used before for partial fraction expansion. And so we can multiply both sides by whichever one. I'm going to start with 3. And then we set j omega equal to minus 3. And so this becomes 5 times 10 to the minus 3 times minus 3 all over 2 minus 3. And so this ends up giving you the value for A, which is 15 times 10 to the minus 3. And then doing the same thing with 2 plus j omega, and then set j omega equal to minus 2. That will give 5 times 10 to the minus 3 times minus 2 all over 3 minus 2. And this gives the value of B, and that is a minus 10 times 10 to the minus 3. So now our IC equation is 15 times 10 to the minus 3 over 3 plus j omega, and then a minus 10 times 10 to the minus 3 over 2 plus j omega. And so we can use the same transform again. And translate this back into the time domain. So IC of t will equal 15 times 10 to the minus 3, e to the minus 3t, and then minus 10 times 10 to the minus 3, e to the minus 2t times u of t. In amps. Okay, questions? Yes.
Is there a reason that you turned it into the j omega before doing partial fraction expansion? Or can you leave it in S domain for?
You can just leave it in the S domain. It's going to be the same. It's probably easier to look at in the S domain.
It's kind of, I was curious if there's.
Yeah.
Okay.
No, I would probably, I didn't realize that's what I was going to do, so.
Right, okay.
Otherwise, I would have left it in S because it's so much easier to look at S's.
Right.
So,
But isn't the VS in the using, oh wait, never mind.
so VS you can translate, you know, sorry, yeah. This was a J omega. That was actually omega. VS of omega. But you could put it in S if you wanted instead. All right, any other questions? Okay.
There is one.
Yeah.
Why would we ever use Laplace transform rather than Fourier transform?
So
The inverse Fourier transform is a lot more difficult to do than the inverse Laplace transform. So if the initial value situation is easier, the Laplace transform is easier to solve. But if it's not easier, the inverse Fourier transform, a lot of times like mathematicians like to just leave it as this giant messy integral because they can't actually evaluate it.
yeah. So that's basically it, is just, does it look simple enough? Which one looks simpler? And then using that. You know, with calculators and computers now, you know, Fourier is usually the preferred one. And so it just is a little bit messier, but it's easier to understand the steps. Usually from Laplace is why we kind of went that route, is to learn Laplace first. And now it's just translate over directly to the Fourier. All right. So next week, let's go to the settings. Oh, so Bri, you were asking this, that lecture notes column? Okay, are gonna be in there. And then, so Monday, you're gonna watch this direct delta function. And then we'll do a remote lesson on Wednesday. So everybody remote, those online, stay remote. So Wednesday will only be remote only lecture, and then Friday will be remote only. Okay. And then we'll do, Monday again will be the recorded lesson, and then Wednesday and Friday we'll do reviews. Do you guys have requests for particular type of questions to go over on Wednesday and Friday of next week? The hardest ones? Okay, we'll go over some really hard ones. Okay. Yes.
Are you gonna be doing remote office hours next week?
And I apologize, I didn't send out an announcement that I thought I would have better internet, and I did not, so I was not able to hold remote office hours this week. So I will hold some remote office hours next week. Well, Monday, let's see. Will I be able to Monday? So not the Mondays, not next Mondays, next Wednesday, I will hold remote office hours on Wednesdays from 11:45 to 12:45. Okay, so just right after this. And if that time doesn't work, but you still need questions, I'm happy to make arrangements to just meet with you one-on-one for other times. So just email me if you need to. Okay, did you have a question, Kyle? Oh, okay, I thought I saw your hand. All right, any other questions? Okay, so you guys, again, I'll see you remotely next Wednesday and Friday, and then remote office hours next Wednesday, and then, actually, I'll be back by the following Wednesday. So just remote office hours Wednesday only next week.
What does it say exam for? We don't have 4 exams.
Oh, error.
The exam
There
three-
used to be 4 exams?
There used to be 4 exams,
The
yes.
exam 3 says March 22nd too.
Yeah, I know the dates are all weird, but it's okay.
Exam, which one says?
Exam 3, or
Exam 3.
if you go to like the 3 page on Canvas, it
Uh-huh.
says April 22nd on the side, and then it says March 26th.
Oh, on the typos, okay, sorry.
Figured it should already have it.
Yes, April 22nd.
I missed that.
Thanks. There used to be another review unit at the beginning,
Oh, well.
and so it was, I'm trying to remember, I think it was Thevenins? I think he did Thevenins, and a lot more dependent sources, but I skipped that one.
Thank you.
All right, see you, Carly. Controls.